Hello, my name is Vignesh Sella, and today we're presenting our work on the development of a Nitrox paraffin hybrid rocket engine. We're a team of undergraduate and graduate students from the University of Illinois at Urbana-Champaign and ISA Supero, and our advisor is Dr. Michael Lembeck, also from UIUC. Our project provides us the opportunity to have a first-hand experience with rocketry in a safe and approachable manner. Today, we'll be discussing the motivation, background, and design of our engine and some novel aspects of our work. Before we get into our system design, here's a little more information about us and the background of our project. This is a snapshot of the contributors to our project. Our team is part of the Illinois Space Society, a technical, professional, and educational outreach student organization at UIUC. We are a chapter of the Students for the Exploration and Development of Space, and so our primary focus is to promote space exploration through a variety of educational and engineering projects. One such project is the Hybrid Rocket Engine project, which initially began in 2013 as a way to explore more complex rocketry systems as compared to solids. In 2018, we decided to revamp our project and build the engine we're discussing today. Here's Andrew with why we decided to make such a pivot.
Hello, my name is Andrew Larkey, and I will introduce you to our team's first hybrid rocket engine, the Eugene engine. It will power the Illinois Space Society's 2021 launch at the Intercollegiate Rocket Engineering Competition, also known as IREC, at Spaceport America. IREC is the world's largest student rocketry competition with over 100 competing student teams across a variety of target altitude and engine categories. We will enter IREC in the 10,000-foot target altitude and student research and design hybrid rocket engine category. Our engine will use paraffin wax and a mixture of nitrous oxide and oxygen called Nitrox. The figure at the bottom is an example of IREC launch operations. It shows the steps needed to load propellants, boot avionics systems, launch, and then recover the rocket structures and payload.
Hi, I'm Abhiraj Majumdar, and I'm going to be talking about the novel oxidizer that we've chosen. So the initial design of our engine made use of a pure nitrous oxide paraffin combination, since both of them are relatively non-toxic, cheap, and widely available. However, during the engine design phase, it became quite evident that the pure nitrous oxide is rather prone to decomposing in the feed system, which then causes critical failures. Nitrox, a mixture of nitrous oxide and dissolved oxygen, offered an alternative that didn't require a complete redesign of the engine and allowed for safer operation, since nitrox has a higher minimum ignition energy than pure nitrous oxide. Another advantage that using nitrox confers is the fact that its vapor pressure can be set during the manufacturing process. Since we want the safety benefits that nitrox offers, a non-negligible amount of oxygen needs to be present in the vapor phase. However, to ensure that the flight oxidizer tank isn't too heavy, the pressure of nitrox has to be set relatively low, which we've set to 45 bar. In order to maintain some amount of oxygen in the vapor of nitrox, it had to be cooled down. Since we're using a simple water ice bath for cooling, we can cool the system to only 0 degrees Celsius. So we've set our design point to 0 degrees Celsius and a pressure of 45 bar. So at the design point, there is approximately 18 to 20% oxygen mass fraction in the vapor phase of nitrox. And at that point, we see from the second figure that there is a substantial increase in the minimum decomposition energy at our design point. On calculating, we find that there is approximately a 50-fold increase in the minimum decomposition energy of nitrox compared to pure nitrous oxide.
Clearly, nitrox is advantageous in terms of safety. However, we also wanted to compare its performance. In this figure, we can see CEA data for the comparison of ISP and OF ratio of a 96% nitrous oxide, 4% oxygen blend, referred to as nitrox 96, and plain nitrous oxide. It is of note that two compositions of fuels are also being compared here. One with pure paraffin wax, and the other with a 40% aluminum additive. We'll be exploring both fuel compositions, but initially we plan to work on a pure paraffin grain only. As for performance, there is a marginal performance benefit of utilizing nitrox over plain nitrous. But as mentioned earlier by Abhiraj, our primary concern is the safety of the oxidizer. So to summarize, nitrox is safer than N2O due to its higher minimum ignition energy. It has a marginally higher ISP and can be used as a drop-in replacement for N2O at similar OF ratios. Thus, we decided to switch over to nitrox 96, and as mentioned previously, it would be kept at 45 bars and 0 C. This entails that we must in fact cool it, and we will be doing so passively through a light thermally insulative jacket around the flight tanks. The engine will also be self-pressurized by virtue of Nitrox's high vapor pressure, and thus we will not have any external pressure in interacting with our Nitrox.
Hello, my name is Nicholas Rasmont, and I'm going to present you a literature review of Nitrox paraffin hybrid propulsion systems. Nitrox is an oxidizer which was first described by Dr. Asif Karabayoglu in his 2009 paper, Nitrous oxide and oxygen mixtures as oxidizer for rocket propulsion applications. This seminal work theorized the concept of nitrox and calculated its physical properties in function of temperature, pressure, and oxygen to nitrous oxide ratios. A follow-up study in 2011 by Chandler et al. Highlighted the benefit of nitrox for a Mars ascent vehicle applications against the baseline solid propulsion, notably its higher specific impulse, its throttling capability, and its thermal stability at Martian temperatures of minus 60 degrees Celsius. In the following years, nitrox studies have been actively pursued at Utah State University within the Whitmore group. Stoddard and Whitmore reported on the results of 16 nitrox ABS test firings, which demonstrated stable, efficient combustion, a potential vacuum specific impulse of 300 seconds, and low engine ignition requirements. However, there is currently no paraffin nitrox hybrid engine firing described in detail in the literature, with only passing mentions to 900 newtons nitrox paraffin tests made by the Space Propulsion Group in Chandler et al. While nitrox paraffin data is sparse in the literature, the properties of paraffin as a hybrid fuel have been widely explored, both in experimental, theoretical, and system studies since its description by Dr. Karabayoglu in 1997. These studies have demonstrated its very high regression rate compared to more traditional HTPB fuels. Other advantages include its high energy density and environmental friendliness. Due to their similar composition, the properties of nitrox paraffin combinations is expected to be correlated to the behavior of nitrous oxide paraffin. Most relevant to all projects are large-scale flight test programs, of which two examples are available in the literature. First, the Peregrine sounding rocket, a collaboration between NASA and Stanford University, which was ongoing as of 2017, and aimed at launching a payload to an altitude of 100 kilometers using a nitrous oxide paraffin hybrid engine. The project succeeded in achieving stable, high-efficiency combustion during ground testing, but has not yet reached the flight test phase. Secondly, the HEROS rocket project from Stuttgart University student group HiEnd, which reached an altitude of 32.3 kilometers during its launch using a nitrous oxide paraffin engine. These examples prove that the development of a nitrox paraffin hybrid with the performance level required for IREC is achievable. However, some key challenges were identified from the reported experience of student group working with paraffin hybrids, namely the Mississippi State University Squidworks and the Atlantis team from the University of Calgary in Canada. They report that the poor structural properties of paraffin fuel grains can result in fuel sloughing under launch conditions. This effect can lead to nozzle obstruction and/or decreased combustion efficiency and stability.
We'll now begin to discuss a system overview. The Eugene engine is approximately 5.5 feet tall and weighs nearly 55 pounds. It will burn for 4.5 seconds at a thrust of 4 kilonewtons. Due to the self-pressurizing nature of nitrox, there is no need for a turbopump or another pressurization system. The feed system features a remotely actuated ball valve for regulating the oxidizer flow and ends with a shower head injector. Nitrox then enters the combustion chamber and is ignited with a pyrotechnic ignition system. The combustion chamber features a single-port paraffin wax fuel grain and an ablative thermal protection system made of canvas phenolic to protect the aluminum chamber body. Combustion products then exit the engine through a graphite nozzle.
Hi, my name is Myron Liu, and I'll be giving a brief mechanical design overview of the oxidizer tank. As previously mentioned, the oxidizer tank will contain Nitrox 96 at a storage pressure of 45 bar at 0 degrees Celsius. It must be made out of a material resistant to the oxidative effects of nitrox and have a high strength to weight ratio. For the aforementioned requirements, The oxidizer tank body is composed of commercially sourced aluminum 6061 T6 tubing. The tank will have flat end caps, also machined from aluminum 6061 T6, and were chosen over elliptical end caps for comparative cost-effective machinability at a relatively low weight penalty. The end caps will be secured to the tank body with 16 quarter-inch bolts, and the sealing medium consists of radial Teflon O-rings. The design is shown to the left. Due to the high vapor pressure of nitrox at higher temperatures, a pressure relief valve with an actuation threshold of 100 bar is employed as a failsafe.
Hi, my name is Zavar Abdi, and I'm talking about the feed system. As mentioned earlier, due to the high vapor pressure of nitrox, we're using a self-pressurized feed system. This architecture is significantly more simple than turbopumps or an external pressurant, and can still provide stable mass flow rates. We elected to use 316 stainless steel for the majority of the piping and valves due to its pressure and temperature resistance. To avoid any leakage in the system and allow for easy assembly, compression fittings were used at most of the connections instead of NPT fittings. All of the components were sourced from commercial manufacturers. To allow for flow control during engine operation, a servo motor operated ball valve is used here, in between the oxidizer tank and the combustion chamber. In the case of the pressure chamber spiking above the upstream pressure, injector pressure, a check valve is used to ensure unidirectional flow. In the case of a hung fire, a solenoid valve will leak nitrox out the piping so the team can safely approach the lines. Finally, there is a pressure transducer right above the injector plate, allowing us to characterize the performance of the injector.
Our injector atomizes and disperses the oxidizer into the combustion chamber. It is a showerhead injector with straight, sharp-edged orifices. We recently planned on chamfered edges, but decided to first try straight edges due to the cost and tolerancing. The material is aluminum 6061, and while it will be exposed to the combustion chamber, we expect the short burn time and active cooling provided by the oxidizer flow to be enough to keep it cool. We consider the oxidizer flow to be single-phase incompressible, rather than two-phase, due to the increased complexity in the two-phase equations of state. We expect that due to the temperature of our stored nitrox and its pressure, there will not be significant vapor phase in our orifice. Thus, our single-phase incompressible analysis should in fact be accurate. To test this, our injector will be verified through our cold flow testing series, expanded upon later.
Atomized nitrox exits the injector into the combustion chamber, where the pressure sits at 30 bar. The chamber is assembled from a commercial body tube and is capped by the upper injector plate end cap and a nozzle retainer ring, which also serves as a nozzle extender to reach our desired expansion ratio. Aluminum 6061 T6 is used for the body tube and the end cap due to its excellent tensile strength, while 304 stainless steel was chosen for the nozzle retainer for its high service temperature. The aluminum chamber body is protected from high temperature by the canvas phenolic thermal protection system, which binds the tube's walls. Inside the thermal protection is our paraffin wax single port fuel grain and a pyrotechnic ignition system.
Hello, my name is Ashish and I'll be talking about the fuel grain being utilized by Eugene. The fuel grain will initially be manufactured of pure paraffin wax. Various hybrid engine studies point towards using hydrocarbons as solid fuels, with paraffin being the best choice for its high regression rate, almost 3 times greater than HTPB, commercial availability, and cost benefits. For simplification purposes, a regular circular port geometry was chosen with the following regression rate model for nitrous paraffin hybrid blend, resulting in the following grain dimensions. Furthermore, manufacturing a perfectly homogeneous fuel grain is quite challenging. Paraffin itself tends to present volumetric shrinking while going through a phase change from liquid molten wax state to a solid structure. As mentioned previously, multiple paraffin wax using engines have also shown chunks of wax exiting the nozzle during hot fires, resulting in slowing. This can be tackled by using structural additives such as LDPE or ethyl vinyl acetate. Mixing any additive such as aluminum or LDPE/EVA into the fuel grain is difficult, as the particles usually settle in the bottom of the grain, since they are heavier and paraffin has a relatively low viscosity itself. Due to these concerns, the team has decided to first test pure paraffin wax fuel grains that will be casted by pouring wax into canvas phenolic directly, which will be supported by a 3D printed structure. However, the objective of the team is still to launch with a 40% ale plus 60% paraffin composition in IREC 2021, which will require a spin casting mechanism previously developed by the ISS subscale hybrid engine team. Adding aluminum grain further improves the combustion process as it increases the reactivity as well as the exothermic heat release due to its relatively high thermal conductivity, which further improves the regression rate, yielding in a better performance of the engine as verified by the CA data.
The function of the thermal protection system is to keep the combustion chamber structure under the maximum operating temperature of aluminum at 100 degrees Celsius. For this purpose, CE canvas phenolic was selected for its combination of desirable properties. It is reported to have good ablative properties, as the phenolic resin forms a dense char layer when exposed to hot gases. It has a relatively low thermal conductivity of 3.5 watt per meter per Kelvin. It is easily available commercially, in contrast with carbon phenolic and silica phenolic composites used on industry-grade solid rocket engines and heat shields. And last but not least, it was used successfully on several student hybrid rocket engines of the same scale and type as Eugene. The thermal protection system is itself structured into three main components. The body tube layer, which covers the entire length of the combustion chamber with a thickness of 1/4 of an inch. Two reinforced sections at the aft and front mixing chambers, which add a 1/2 inch layer of phenolic to these zones for a total of 3/4 of an inch. This added protection is made necessary by the higher thermal fluxes experienced in these areas. And finally, a 1/4 of an inch thick plate to protect the top end cap. These thicknesses were chosen based on reported thickness used in comparable student hybrid projects. Validation of this design will be conducted through thermal finite element analysis modeling and testing, which will allow us to fine-tune the thickness needed in different parts of the engine.
The team elected to use a simple conical nozzle with a 15-degree half angle over a bell nozzle due to the manufacturing costs and logistics required with a more complex nozzle shape. A conical nozzle is simple to manufacture while still providing appropriate performance for our applications. We considered two materials when designing the nozzle, graphite or a canvas phenolic composite. We also debated whether to use a combination of two materials with graphite in the throat area and the canvas phenolic in the converging and diverging sections. Ultimately, we decided to use a monolithic graphite nozzle design. This design has been used successfully on other hybrid rockets of similar scale. Even though graphite is heavier than canvas phenolic, its use simplified our design while still providing effective erosion minimization. Using NASA's CEA in the design of our combustion chamber, we were able to calculate the required parameters to accurately dimension our nozzle. These are included in the next slide, along with the CFD analysis used to verify this design.
Since the design parameters for the nozzle needed to be verified, a CFD simulation was done using ANSYS Fluent. The fluid properties were calculated using the exhaust gas composition that was provided from the CEA results. Then using all the results from the CEA analysis, a simple 2D axisymmetric simulation assuming a viscous and calorically perfect gas was done. From this first contour plot, we can see that the exit pressure of the nozzle is approximately atmospheric. Hence, the converging diverging nozzle is appropriately expanding the flow to nearly perfectly expanded. Another value from CEA was the exit Mach number from the nozzle. From the second contour plot showing the Mach number, we can see that the exit Mach number is also close to the CEA calculated value of 3.
I'm Avinash Rao, and I will be speaking on the testing plan for Eugene. So for our testing series, we consulted and coordinated with the staff at Purdue's Zucrow Laboratories. Their expertise and facilities were critical in designing a comprehensive testing program that was in line with technical and safety standards. The program will consist of high-pressure testing of our feed system, a cold flow test, and hot fires of the engine. For the full testing series, a modular and portable test stand was designed, utilizing standard 1-inch 80/20 rails and other commercially available components. The test stand can be set up in different modes to facilitate each test in the series. Seen here is the hot fire configuration of the stand. Before cold flow and hot fire testing, the calibration of the pressure transducers and the verification of the main ball valve actuation must be completed. The high pressure N2 testing allows us to build that calibration curve by slowly pressurizing the line and noting the values of a pressure gauge and the signal from the pressure transducers for a series of values. This test also allows us to test the actuation of the main ball valve. Once the data for the calibration curve has been obtained, we vent the lines by actuating BV101. We repressurize the line several more times to ensure proper actuation of the servo motors and diagnose any issues at this step. Should BV101 fail to actuate under high pressure, we then manually open the safety ball valve, BV203. Our next test in the series is a cold flow, which primarily allows us to confirm the mass flow rate through our feed system as well as the discharge coefficient of the injector. Since this test is also our first opportunity to observe pressurized oxidizer flow through the feed system, cold flow also serves as a validation of the structural integrity of the tubing while experiencing operational conditions. Data collection will consist of a weight scale under the nitrox tank and pressure transducers at indicated positions in the feed system. Qualitative data will also be collected in the form of video recordings to assess the structural integrity of the feed system in addition to the flow distribution of the injector. The test is determined to be a success if we can confirm our mass flow rate and discharge coefficient are within 15% of our expected values of 1.54 kilograms per second and 0.7 respectively, and no significant jitter or leaks are observed in the feed system. Hot firing of the engine provides the opportunity to verify that the engine fires without any significant issues and allows us to characterize the thrust generated. The test will primarily determine that the engine is capable of providing the expected thrust for the total expected burn time. Data will be collected in the form of load cell measurements, allowing us to construct a thrust curve to characterize the engine's performance. In addition, pressure is monitored at the indicated points, and any significant deviations from expected values at these points will be noted. The test is determined to be successful if we can observe a burn time within a half second of the expected 4.5 seconds and a peak thrust value within a 50% margin of error of the expected 4 kilonewtons. It is of note that the hot fires will be performed with the exhaust directed upwards, thereby simplifying our test stand design.
As fall begins, the team will immediately work to continue the test campaign, as this is our main priority. Once a successful static hot fire test is achieved using a pure paraffin fuel grain, we will work to conduct an additional test utilizing a fuel grain consisting of 60% paraffin and 40% aluminum powder. As previously noted, the aluminum additive will help to greatly increase our ISP. A spin casting machine using a wood lathe to provide rotational motion will be required to manufacture this fuel grain, and work on this manufacturing method will be in parallel to testing of the engine system. In an effort to promote open source learning and documentation, the team has been documenting a more detailed account of the work done on this engine in a public wiki page hosted by University of Illinois servers. We use it as a one-stop shop reference for design iterations and hope that others continue to add to it in the future, and that anyone can use it as a guide to designing a hybrid engine from scratch. This spring, we will begin to integrate our engine into the body of our rocket in preparation for our first flight in June 2021 at IRAC. Lastly, a long-term goal is utilizing the potential of throttling. The main ball valve was designed with the capability of real-time throttling to create variable thrust output. This would require a deeper understanding of how the flow rate affects thrust in the development of a robust real-time control system.
We'd like to thank the Student Sustainability Committee, Office of Undergraduate Research, Illinois Space Society, and Department of Aerospace Engineering for their funding, resources, and support. We're also grateful for the School of Chemical Sciences Machine Shop, Zucrow Laboratories, and Christopher D. Nielsen at Purdue University, Dr. Stephen A. Whitmore of Utah State University, and Dr. Dasu Nagasu of the Aerodynamics Research Lab at UIUC for their technical support. And thank you for watching and listening. Listed here are the references we've used throughout the presentation. Thank you.